Search in rotated sorted array. Let's raise the stakes. What if the array you're searching in is sorted, but then suddenly rotated at an unknown pivot? Search in rotated sorted array is a Pattern Mastery 100 superstar and a go-to interview question at Google, Facebook, and Apple. So many candidates try to flatten the array or revert to brute force, but with the right approach, you can use binary search to find any target in O log n time. Mastering this pattern proves you're ready for real-world coding challenges. Let's see how it's done. Let's break it down. You're given a sorted array that's been rotated at an unknown point, and a target value. You need to find the index of the target, or return -1 if it's not present. No duplicates, and the array is still mostly sorted, just with one pivot. Now let's assess. Scanning every value is not good enough for large arrays. Because the array is made of two sorted halves, we can adapt binary search. At each step, we determine which half is sorted, then see if the target lies within that half. This halves the search space each time. Classic O log n efficiency. Here's the structure. First, set left and right pointers at the array's ends. Then, while left is less than or equal to right, find mid. If nums at mid equals the target, return mid. If nums from left to mid is sorted. If the target is in this half, move right to mid -1. Else, move left to mid +1. Otherwise, meaning the right half is sorted. If the target is in this half, move left to mid +1. Else, move right to mid -1. Finally, if not found, return -1.
Let's try to implement it using Solution 1. We begin by defining the solution class. This is simply the container that will hold our method. Then we declare the search method. It takes in a rotated sorted array and a target value that we want to locate. Next, we start a simple loop that walks through the array from left to right. Since we check each element exactly once, this loop runs in linear time. Inside the loop, we compare the current element with the target. If the value matches the target, we immediately return the current index. This means we have successfully found the target and can stop searching. If the loop finishes and we never find the target, we return -1. This indicates that the value does not exist anywhere in the array. And that's how this algorithm works. It checks each number one by one, returns the index as soon as it finds the target, or returns -1 if the search reaches the end. Efficient, simple, and elegant. Check. This test verifies the search in a rotated sorted array function. Nums equals 4, 5, 6, 7, 0, 1, 2. Target equals 0. The array is sorted but rotated, and we want to find the index of the target value. Looking at the array directly, index 0 has 4, index 1 has 5, index 2 has 6, index 3 has 7, index 4 has 0, index 5 has 1, index 6 has 2. The value 0 appears at index 4, so the correct result is 4. The output is 4, matching the expected 4. This confirms the search logic correctly identifies the target in a rotated sorted array. Now let's try another implement approach using Solution 2. We begin by defining the solution class. This is just the container for our method. Then we declare the search method, which takes the rotated sorted array and the target we are trying to find. Next, we create two pointers. L starts at the far left. R starts at the far right. These mark the boundaries of our current search window. After that, we begin a binary search loop. As long as L has not passed R, we keep narrowing the range. Because we cut the search space in half each time, this runs in log n time. Here we compute the midpoint M. This is the index we check to decide which direction to explore next. First, we check if the midpoint already equals the target. If it does, we return M immediately. The search is complete. Next, we check whether the left half is sorted. If the value at the left pointer is less than or equal to the value at the midpoint, then the segment from left to midpoint is in sorted order. Now we ask if the target lies inside that sorted left half. That means the target is at least the left value and strictly less than the midpoint value. If that is true, we move the right pointer to just before the midpoint. Otherwise, the target cannot be in that left sorted half, so we move the left pointer to just after the midpoint and search the right side. If the left half is not sorted, then the right half must be sorted instead. Now we check if the target lies inside the sorted right half. That means the target is greater than the midpoint value and at most the right value. If that is true, we move the left pointer forward to search the right side. Otherwise, the target must be on the left side, so we move the right pointer backward. If the loop finishes without finding the target, we return -1. This tells us the target is not in the array. And that's how this algorithm works. It uses binary search, checks which half is sorted, and only searches the half where the target can actually exist. It repeats until the value is found or the range collapses. Efficient, simple, and elegant. Check. This test confirms the behavior when the target is not present. Nums equals 4, 5, 6, 7, 0, 1, 2. Target equals 3. The first portion, 4, 5, 6, 7, is too large for 3. The rotated portion, 0, 1, 2, is too small for 3. There is no position where 3 appears. A rotation-aware binary search reaches the same conclusion by narrowing the search space until nothing is left to search. So the correct output is -1. The output is -1, matching the expected -1. This confirms the solution correctly reports that the target is absent.
Let's have a quick recap. Breakdown recap. This problem takes a sorted array that's been rotated at an unknown pivot and asks us to find a specific target value. The catch is that while the array looks broken, each half is still sorted, meaning we can use logic, not brute force, to locate the target efficiently. Assess recap. At first glance, it's easy to fall back on a linear scan, but that's ON time, too slow for big inputs. The key insight is realizing that even after rotation, the array keeps a sorted structure in parts. By identifying which half is sorted during each step, we can adapt binary search to work perfectly here. Structure recap. The solution's flow revolves around 2 pointers, left and right. We repeatedly find the midpoint, check which half is sorted, and decide where to move next. If the target falls inside the sorted range, we search that half, otherwise, we shift to the other. Each step cuts the search space in half. Implement recap. When we ran the algorithm, the process played out like a guided binary search with added logic. At every iteration, we evaluated which half was ordered and adjusted our search boundaries accordingly. The code naturally zeroed in on the correct index, or concluded that the target wasn't present. Check recap. Testing the algorithm on our example confirmed the reasoning. The search quickly honed in on the target value of 8, found at index 5. Every comparison narrowed the field with precision, proving the O log n efficiency we expected from binary search. The biggest takeaway here is that patterns matter more than appearances. Even when an array seems broken, its underlying structure holds the key. Recognizing that lets you transform classic techniques, like binary search, into powerful tools for complex problems. Once you see this pattern, you'll never look at arrays the same way again.